the alkaloids. You have come across the classification of the alkaloids and the method of isolation, how we can exploit the nature of the alkaloid. Alkaloids are nitrogen containing, which are good bases. That's why they are bitter in taste, because all bases are bitter in taste. So because they are amines are bitter in taste. So these compounds resemblance to such are called alkaloids, mean alkali-like. This terminology, alkali-like, was first derived from a scientist, a German scientist. Let me write his name. It was Meissner. Meissner, and in 1819, basically, he first of all used this terminology. So first terminology about these concepts were built up in 1819. You can see almost 2 centuries back, the alkaloids were named. Mean they were called alkali-like because they were bitter in taste. Mostly these are present, these are been isolated in the form of salts of the acids. Why? Because they are bases. So in plants, the acids are also present. So plants, acids and bases, these alkaloids and bases, they get protonated. Once they get protonated, they become salt, and salts are highly soluble in water, if you remember, because water is a polar solvent which dissolves the anion and cations. So in most of the form in the plants, the alkaloids are in protonated form. They may be the salt of acetate because acetic acid is present. They may be the salt with oxalate, mean oxalic acid, mean tartaric acid with tartarate, malonic acid as malonate, and similarly citric acid as citrate. So these can be the salt with acetate, oxalate, tartarate, malonate, or citrate. Normally, maybe any other salt they may have. But when we react them with sodium bicarbonate solution, you have seen as per scheme. So these get neutralized and they are present in pure state, not in the form of salt state. So when we isolate, they are not in protonated form. But when we isolate it from plant, they are in salt formation. So anyhow, this is just a introduction you have come across in previous lecture, and you have seen the isolation of this. Now, one method is used to detect the alkaloids in the plant. This is a very diagnostic test. Just like some tests we have come across in the salt analysis are commonly called diagnostic test, or the confirmatory test. With anything else doesn't give such test. It's called a diagnostic test. Right? So let's see if I present, if we are interested to separate alkaloids from other or identify alkaloids from the other. So one method is very interesting, which is called using we carry out the TLC of the plant material, and then we run this on TLC. So we put a spot of the extract, we run the TLC, and then we spray a reagent commonly called Dragondorff. So let me first, if I present Dragondorff. This is called Dragondorff's reagent. Dragondorff's reagent. So what is Dragondorff's reagent? Dragondorff's reagent is basically, it is bismuth nitrate. It is bismuth nitrite, not nitrate, nitrite. This is bismuth nitrite. What is the role of this bismuth nitrite? So this Dragondorff reagent basically is composing of, so Dragondorff reagent. This is the composition of Dragondorff reagent, which consists of barium nitride. Barium nitride is basically the active constituent in this. What happened in this? Bismuth, if you remember, where lies bismuth? Anybody know? In which group is it? No one knows. Bismuth is non a transition or an inner transition metal. This is present in P block. If you go to the nitrogen family, just in the end of this. So nitrogen family contains nitrogen, phosphorus, arsenic, antimony, and bismuth. Bismuth is the last element in this group. So it is present in nitrogen family. So bismuth is a metal, in fact, like we have come across Sb, commonly called stabium. So stabium and bismuth, similarly arsenic, all these three are metals, but not called metals because they have properties similar to metal and metalloid and non-metal. So that's why they are called metalloids, if you remember. So bismuth is included in that. Bismuth, antimony, arsenic, all of them are metalloids, right? So which has the properties of metals and non-metals. So if we look at nitrogen is a non-metal, but bismuth act like a metal and non-metal both. So what is the role? Basically, the alkaloids you have come across, let's say if I draw the structure of a 5-membered ring, if I show nitrogen is present here. So this nitrogen is present in the form of this ring, a 5-membered ring. And similarly, if I show right, I'm just going to show this while it is coordinating with bismuth, right? So bismuth, you can see this is coordinating with both of these entities. Let's see, nitrogen coordinates with bismuth. Now you can see in this case, let's see, I am just going to magnify this so that you can see easily. This is a Dragondorff reagent. Dragondorff reagent is barium nitride. Basically, when this barium nitride in acidic medium, it is prepared in sulfuric acid, dilute sulfuric acid. So we have a dilute sulfuric acid and we add barium nitride to that. So it produces barium ions in that. These barium ions, once they are separated on TLC plate, so we get a purple plate, bismuth nitrate, as its color is presenting. Why I made this magenta color? Because when we separate this on TLC, it make all TLC this magenta colored. And when we heat the TLC, so what happened? This nitrogen coming from any alkaloid, not 5-membered ring only alkaloids, all kind of alkaloids. The purpose I am presenting is nitrogen is present in them. So that nitrogen, basically, two of them makes a bond, coordinate covalent bond to the bismuth. So this is the coordination chemistry. You have already come across in previous classes in inorganic 1 and inorganic 2. So in this case, it coordinates with this and generates a complex, because bismuth is acting here as a metal. Although it has no d electron, but it has electron accommodated by these nitrogen in pp, right? So that's why they are having they show a color. On this color basis, the terpenite doesn't show this color because they don't have nitrogen present in them. Similarly, flavonoid and many other natural products you shall see shall not give you this test positive. Only and only alkaloids give this test positive. This is the characteristic of the alkaloids, that they give you this test. So this is a very easy method. If you are interested to calculate either your compound contain, either your plant you are interested in, you are working on, that contains alkaloid or not, this is the best test to perform it. I hope it shall be clear right now. So now I shall switch over to the biosynthesis of the of the alkaloids. Keeping in mind, just like you have seen for the terpenoids, you have seen that mevlonic acid leading to the isoprenyl unit. The isoprenyl unit is the basic precursor of the terpenoids. And it is originating from mevlonic acid, which is originating from glucose. So you can say glucose converts into mevlonic acid. Mevlonic acid converts into isoprenyl alcohol. That alcohol is protonated. It is been reacted with one ATP molecule, which converts into AMP, transferring to phosphates, converts that into isoprenyl pyrophosphate. That isoprenyl pyrophosphate further combines. You have come across in previous lectures, 4-5 weeks, that how a variety of terpenoids are being synthesized by these type of isoprenyl unit. But what are the precursor for alkaloids? Keeping in mind, the precursor for the alkaloids are basically simply these are amino acids. You have already come across about amino acid. The amino acids combine to form proteins. And these proteins are very essential. They are in primary metabolites, right? So glucose, which is a basic precursor of the terpenoids, is also basically primary metabolite, if you have come across. Similarly, the basic precursor of alkaloids and terpenoids, they are not primary metabolites. They are secondary metabolites, but they are originating from primary metabolite. Terpenoids are originating from glucose. Alkaloids are originating from amino acids. Let's see, I have introduced a variety of different components. Let's say if I present you here one alkaloid, one amino acid that you are already familiar with. Let's see. Right, I hope you are familiar with the structure. This is commonly called, no, I'm just initiating the biosynthesis of such compounds. So this is basically, let's say, this is an amino acid. If you remember, this is commonly called S-alanine, if you are familiar with this. And S always is italicized, but this S is showing, the absolute configuration. Mean this nitrogen is this is an asymmetric center. You can say this S is associated with this asymmetric center, showing this is anti-clockwise. Nitrogen is our first priority. This carbonyl group is second priority. This CH2 group is third priority. You have come across about CIP rule in your semester 5, organic chemistry 1. And this hydrogen, which is the pointing here, is behind the plane. So this is 1, 2, 3. You can see this is the anti-clockwise rotation. So this is a S-alanine. Keeping in mind all amino acids that the nature produces are S in configuration. The nature doesn't produce R amino acids. I'm not talking about only alanine or not phenylalanine. Sorry, this is not aniline. This is phenylalanine. I should have meant phenylalanine. If this is, let's say, if this phenyl is not present here, so we have a CH3 group here. Sorry, only this CH3 group is here. So this is called S-alanine, but this is called phenylalanine. But alanine is also having S absolute configuration. It is also having S absolute configuration. It means in all amino acids, if we are presenting it like this, alkyl group is on this, carboxylic is on this, and this amino group is at alpha position to carboxylic. It will always be above the plane in S. If this is behind the plane, it shall be R absolute configuration. But the nature only produce S absolute configuration. We have less than 1 minute remaining. We shall log in again.